Hello everyone, this is Sri Guru over here. Welcome back to my YouTube channel. Today we are going to start a new chapter called Semiconductor Electronics. The total number of teaching hours 12 and the weightage of marks 10. Okay, the first concept of this chapter, this is the basic. This is one of the interesting and the conceptual based chapter. Band theory of solids. Inside the crystal, each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electrons will have a different energy levels. These different energy levels with a continuous energy variation from what are called energy bands. Electrons occupy energy states in atomic orbitals. This means there are well-defined energy levels of electrons in an isolated atom. But when several atoms are brought close to each other in a solid, these energy states split up into series of energy states called molecular orbitals. The spacing between these states are so small that they overlap to form the energy bands. The farthest band from the nucleus is filled with the valence electrons and is called as a valence band. The empty band is called conduction band. The energy of the highest filled state is called Fermi energy. There is a certain energy gap called forbidden energy band gap, and it is represented by delta G, which appears between the valence and the conduction band. And here you can see the explanation of the band theory as we did in the earlier. Look at here. Here p and s orbits are going to interact this along the x-axis. Here we are choosing the interatomic distances, and along the y-axis we are choosing energy. As p and s are get overlapped because of the overlapping of energy levels, there is a well-defined modifications takes place, and that form the conduction band here, and there is a valence band below here, and there is a gap between the conduction and the valence band, which is known as a energy band gap. Primarily, four types of band structures exist in solids. In metals, the valence band is either partially filled or the valence band and the conduction band is overlapped. In case of insulators and semiconductors have completely filled valence band and empty conduction band. It is a magnitude of band gap which separates metals, semiconductors and insulators in terms of their electrical conductivity. Energy gap between the conduction band and the valence band is given by delta Eg is equals to conduction band minimum minus valence band maximum. And there is no presence of free electrons in between the conduction and valence band, that is a forbidden energy gap. Width of the forbidden energy gap depends upon the nature of the substance. This means it does not constant for all the materials. It is different for different materials. As the temperature increases, forbidden energy gap decreases very slightly, and that can be observed by using this diagram. That explanation regarding the first metals, as you can see here, the conduction band and valence band, there is no band gap. Either in case of metals they are partially filled or they just overlap, as we discussed in the earlier. By applying the small amount of external energy by using the battery, we can make the electrons to shift from the valence band to conduction band, and these electrons are the charge carriers, and they can easily move in the direction of opposite to the direction of applied electric field. But in case of insulators, The energy band diagram of insulator is shown here. Here the valence band is completely filled. The conduction band is empty and energy gap is quite large. It is more than 3 electron volt. For example, diamond is having 6 electron volt energy gap. Due to the large energy gap, no electron is able to go from the valence band to conduction band even if electric field is applied. Hence, electrical conduction is, in this case, material is impossible and they have behaves as a insulator. But in case of semiconductors, the energy band diagram of the semiconductor is shown. Here also the valence band is totally filled and the conduction band is empty, but energy gap between the conduction and the valence band is quite small. It is less than 3 electron volt. For germanium, this band gap is around 0.72 electron volt, and for a silicon it is 1.1 electron volt at a 0 Kelvin temperature. Electrons are not able to cross even if a small energy gap, and hence the conduction band remains totally empty. Therefore, semiconductor at a 0 Kelvin behaves as an insulator. However, at a room temperature, some electrons in the valence band acquire thermal energy greater than the energy band gap less than 3 electron volt and jump to the conduction band where they are free to move under the influence of even a small electric field. As a result of it, the semiconductor acquire a small conductivity at a room temperature. The resistance of the conductor would not able to high as that of the insulator. Thank you for watching my video. Don't forget to like and share and subscribe. Thank you.